The Spectrogram Classification Part 2. The tutorial starts with an explanation of the significance of specific frequencies in understanding different sleep phases. Moving on to Section 2, the tutorial concludes with illustrative examples of sleep spectrograms. Section 1. Important sleep frequencies in the spectrogram. Here we observe a full night sleep spectrogram. In the spectrogram we can distinguish different frequency bands. The sigma band from 12 to 15 Hz, the alpha band from 8 to 12 Hz, the theta band from 5 to 8 Hz, and the delta band from 0.5 to 5 Hz. Understanding these bands is crucial for pinpointing and interpreting different sleep stages. Let's now analyze the wake stage. To get a closer look at wakefulness, let's zoom into a part of the full night sleep spectrogram. When someone is awake, there's a lot of activity in the alpha band 8 to 12 Hz. For some individuals, activity in the alpha phase may be double, meaning that you will observe two red areas in the alpha band, as shown in this segment. On the other hand, the activity can be also single, meaning that you will observe one main red area in the alpha band for wakefulness. In the example, you can notice the transitioning from being awake to entering non-REM sleep because the alpha activity decreases. In this 1 hour segment, it's easy to see and understand the difference between wake and non-REM stages just by looking at the spectrogram. Let's check out another part of the full night spectrogram. Keep an eye on the activity around 8 Hz. Sometimes, you might see some activity in lower frequencies during wakefulness, which may indicate eye movements. It's important to note these differences between being awake and in non-REM sleep. Remember, when someone is awake, you'll see action in the alpha band. Also, notice a gap in the theta band during wakefulness, while in non-REM, there's activity. This extra detail helps us tell the difference between being awake and in non-REM sleep. Non-REM phase. Here is another example of a full night spectrogram. Let's zoom in to observe the non-REM phase in detail. In this segment, we observe both wakefulness and non-REM phase. Rather than discrete changes in non-REM, we observe a continuum of change. In non-REM, there is a strong growth of delta power. In the full night sleep spectrogram, it is not always easy to exactly distinguish the non-REM stages, N1, N2 and N3. N1 starts with decreasing of alpha activity and increasing of delta. Then N2 follows, and it is characterized by a high activity in the sigma band. Finally, N3 stage or deep sleep is characterized by slow wave activity. During N3, sigma activity may reduce. So far, we have seen the linear scale of the full night spectrogram. This example shows how the log scale spectrogram looks like. The reason to use the log scale is to observe in more detail the lower frequencies in the spectrogram. Let's again zoom in and see how it works. Using the log scale, we can observe the lower frequencies in a higher range. In this segment, we nicely observe the N3 delta power. Furthermore, we can even detect an awakening during the non-REM phase. This log scale tool will be provided to help the spectrogram classification in the experiment. The REM phase. The REM stage is more difficult to identify than wake and non-REM because it does not follow a concrete pattern. However, we can still try to identify it in the spectrogram. The REM phase does not have a lot of features associated with it in the electroencephalogram. However, it's associated with sharp waves from 2 to 6 Hz and mixed frequencies. In this segment, we observe the transition from non-REM to non-REM again. After non-REM, we would expect REM to happen with a decrease of both sigma and delta activity. We can also observe it using the log scale, where we can distinguish the transition from non-REM to REM by the decreasing of delta power. Sometimes, wake and REM phases can be easily confused in the spectrogram. This is why it is important to understand their differences. During REM, activity in the alpha band is reduced. Remember, wakefulness is characterized by high activity in alpha. This is a summary of what we have discussed so far. It is recommendable to use these motifs to identify the different stages in a full night spectrogram. When performing the experiment, you can use this cheat sheet as a guidance to classify the spectrogram. Section 2. Sleep spectrogram scoring examples. This is an example of a full night sleep spectrogram. Let's try to find the wakefulness stage in the spectrogram by looking to the motif. Once we have identified wakefulness, let's continue with non-REM. At this moment, we have identified both wakefulness and non-REM stages through the night. Now the question is, do the remaining segments belong to REM stage? Or we were wrong identifying the stages? Looking to REM motif, we can observe that at least 4 out of 5 of the remaining segments belong to REM. Maybe the first one is not that clear. This is why we are going to observe it in the log scale. This segment comes from non-REM and has a decrease in delta. Furthermore, the activity in the alpha band is low, so we can assign it also to REM. So far, we found 5 REM phases. The REM phase in a classic normal sleep spectrogram should have a longer duration at the second part of the night. In this case, the duration of the REM phase decreases at the second part of the night. Nevertheless, we can conclude that this spectrogram looks like a normal sleep spectrogram because it follows the sleep cycles a total of 5 times during the night without any long interruption. Here we have another full night sleep spectrogram. First, we observe high power in all frequencies at the beginning, which could be made by motion artifacts. In this case, we observe different activity in the alpha band. To differentiate wake from non-REM, we need to observe also the delta and theta bands. Regarding the theta band, we observe a gap in the wake phase, whereas in non-REM there is power. Knowing this, we can identify both wakefulness and non-REM phases. As you can observe, this example is clear an abnormal sleep spectrogram because it has a lot of long interruptions during the night, and we have not identified any REM phase. Thank you for watching. You may proceed with the tutorial.